Hello and welcome to 8.4. We're going to learn 2 additional tests to see if series converge or diverge. We are going to learn the direct comparison and the limit comparison test. Now on the direct comparison, you're going to be looking at 2 series. You're going to be looking at the one you're trying to figure out and then an additional series. All right. It's a little bit tricky, this direct comparison, because you have to know which series is bigger and where it's headed. Okay, so for instance, if you know a larger series converges, then you know the smaller one you're trying to figure out will also converge. Because if the bigger series has a limit, then a smaller series will as well. So in that case, you have to know that a bigger series converges. A little tricky. Now, if you're looking at a compared series and you know it diverges, okay, you're hoping it's the smaller of the series. Because you know if a smaller series has no bound, then a bigger one will also have no bound. So not only do you have to know a series to compare it to, you have to know if that series diverges or converges, and you have to know if it's bigger or smaller than the series you're comparing it to. Okay, so let us see what all this must look like. Okay, so on my first example here, I'm looking at 1 over 2 plus 3 to the nth power. Okay, so I want to find a series that is similar to the one I'm trying to prove. Okay, so I have 1 over 2 plus 3 to the nth, so I just thought maybe I'll compare that to 1 over 3 to the n. I know what's happening there. Okay, I know that's a geometric series, and r is 1/3, because remember you can rewrite that as 1/3 to the nth power. Okay, so by the geometric test, I know that this converges. Now, this converges, so that means hopefully this is the bigger series. Okay, so when I look at the original series and the one I just looked at, okay, I know this one converges. As long as this guy is bigger than the series I'm questioning, I'm going to be okay. And clearly this denominator is bigger, so this fraction is going to be smaller. So sure enough, I know this guy converges, and I know he is bigger than the series I am looking at. So therefore, a sub n must also converge. Okay? Now this can be a little tricky, because for instance, in this example, if I look to do the same thing I did in example 1, and I just look at this guy right here, we'll go 1 over n to the 1/2 power. Okay, so I'm pulling that same trick I did in example 1. Now I know that this is P series. And the P is less than 1, so that means this guy diverges. But when I look at this guy diverges, so this function I'm comparing it to should be smaller. But wait a minute, my function 2 plus square root of n is less than or equal to 1 over square root of n. So to say that the bigger guy diverges, the smaller guy does too, well, not necessarily. Okay, so therefore I can't use this series. So I'm going to have to start from scratch and use a different one. Okay, so I'm going to compare it with, I like P series, so I'm going to go bigger. Okay, now this is a harmonic series, so I know this one diverges, and I know that it is smaller than my 1 over 2 plus square root of n. Okay, so now that makes sense. The smaller series diverges, so you know the bigger one also diverges. So therefore, this series diverges. Okay, so with direct comparison, you're going to come up with a series to compare. Okay, if that series diverges, it better be smaller than the series you're looking at. If it converges, it better be bigger than the series in question. Okay? Okay. So that's why direct comparison can be a little bit hard. Now the limit comparison is a little bit easier. It's good for fractions where the numerator's power is smaller than the denominator's power. And because it's comparison, you are going to need another series. You're going to need one that you know if it converges or diverges. Now, the good part about limit comparison is I don't care if it's bigger than or smaller than the other series. Okay, I'm just picking one I know. And then I'm going to compare it to one that I do not know. Okay, so A sub n is playing the part of the series in question. B is the guy I already know. So B, I already know that guy. I'm going to make that into a fraction. The guy already knows on the bottom. If that equals some number that is positive and finite, then the series you're asking about is going to do the same thing as the series you already know about. Okay, so the L doesn't tell you if it converges or diverges. The L tells you it does the same as the series you picked. Okay, I know that's as clear as mud, so let's do an example. Alrighty, so here we go. Looking at this guy right here, I'm just going to pick something that looks easy. Okay, and as I go to infinity, remember you always check those powers, I'm going to go with a P series again. I kind of like me some P series. So I'm going to compare with this guy. 1 over n to the 3/2 power. Okay, so it's P series. You had an n to the 1/2, n to the second, so that's why I chose 3/2. And I know that since my P is bigger than 1, this is going to converge. Okay. So I'm going to do my limit comparison. I'm going to do my limit as n approaches infinity of the one in question. We want that on top where we can keep an eye on it. And the one I already know about. Okay, I'm going to flip and multiply. I'm just going to change that to n to the 1/2 power for grins. Okay, so if I multiply straight across, I'm going to have n squared over n squared plus 1. Well, I am approaching infinity, so you're looking at the highest powered term on top against the highest powered term on the bottom. They are equal, so this is going to go to 1. Now, this is positive and finite, so the function we're looking at is going to do exactly the same thing as the function we compared it to. Okay, so since B sub n converges, A sub n will also converge. Okay, so therefore, this little guy is going to converge as well. Okay, let's look at another. Okay, this guy converging or diverging. Okay, I'm just kind of looking to see what's going on here. I can't think of a function that fits into a specific name, so I'm just going to look at some powers, and I'm going to do 2 to the nth over n squared. Because you've got n up here, n to the 3rd down here, those would cancel, give me an n squared. I want to keep it simple. Okay. Well, this guy, if we were to see if this converges using my nth term test, I would have to do L'Hopital's rule twice. But your 2 to the nth is going to get bigger faster, so this is going to infinity, which means this guy diverges. Okay, so now when we do our limit comparison, because it does have a limit, The guy we're looking at's on top. The guy we already know about is on the bottom. Okay, so my limits. Okay, now I'm going to go ahead and simplify that n and that n squared there. So I'm going to have 2 to the nth over, no I'm not, sorry, you can't do that. As limits you can, but right now you've still got the plus 1. Time n squared over 2 to the nth. Now the 2 to the nths, I can go ahead and cancel those out because that's multiplication. And then when I multiply that straight across, I don't know why I'm writing at a diagonal today. I guess I'm just a little off. Okay, I end up with n to the third over 4n to the third plus 1. Now when I look at the limit as n approaches infinity, look at the highest power term on top against the highest power term on the bottom. This is going to go to 1/4. This is positive and finite. So my limit, my series is going to do the same thing as the limit I'm comparing it to. So therefore, my limit, n times 2 to the nth over 4n cubed plus 1, is also going to be divergent. Remember, this doesn't tell you it converges to 1/4. This tells us that now this guy is going to, your a sub n, is going to do the same thing as your b sub n. So if he diverges, you diverge. Okay? All right, I will see you back in class for some fun